Now we are moving to the next section, right? So we are here at the carbon-carbon bond making, right? Now we are leading to the next session, the part B, where we are supposed to discuss about the elongating the carbon chain by more than 1 unit, right? Elongating the carbon chain by more than 1 unit. That is what we are going to do now, right? Okay. So let's put that name there. Increasing the carbon number by more than 1 unit, right? Increasing the carbon number by more than 1 carbons, right? More than 1 carbons or 1 unit or more than 1 carbon. Right? So this is our topic for today. Right? Okay. I don't know any other. Right. For this task, we are with 3 techniques to elongate the carbon chain by just 1 unit of carbon. We have 2 techniques now, cyanide method and the formaldehyde technique. We haven't discussed that thing. We'll discuss that thing later. But to elongate the carbon number by more than 1 unit, we have 3 techniques available in our syllabus. Acetylide method, Grignard method, and the condensation method. Acetaldehyde, Grignard, and the condensation. Right? First, we'll start up with the Grignard method. After doing the Grignard method, it is easy to understand the acetaldehyde method. So I'll start up with the Grignard method to elongate the carbon chain by more than 1 carbon. Right? So let's start up with that. Number 2, we'll start off with number 2 in your note. That is Grignard method. Grignard method. Right? First of all, let's discuss the theory behind this technique. Then we can go for the conversions. Right? Okay, actually we have discussed the theory when discussing about the alkynes. Actually, we'll discuss again. Right? Grignard method. So Grignard reagents can be made by 2 reactions. Right? What are the 2 reactions available? So you can come up with the alkyl halide. This see, you can come up with alkyl halide, right? Okay, CH3, CH2, Mg, CH2, CH2, Br. Okay, alkyl halide. If you add some magnesium in dry ether medium, just adding magnesium in dry ether medium to alkyl halide, right? You see, this is your alkyl halide. This is how we are supposed to produce the Grignard reagent, right? So what will happen? So that Mg will connect to here. CH3, CH2, Mg, Br. Right? Simple like that. So another method is there. That is, you can come up with a terminal alkyne. This has been discussed with the alkynes, right? Come up with terminal alkyne, and to that you can add any of the Grignard reagents, any Grignard reagent, right? Any RMGBR, any Grignard reagent. Then you will come up with this thing, another Grignard reagent. Adding a Grignard reagent to a terminal alkyne will produce another Grignard reagent, which is known as the acetylenic Grignard. Acetylenic Grignard. We had discussed this thing with the terminal alkynes, right? So these are the two methods of producing the Grignard reagent. Right? These are two methods producing the Grignard reagent, right? So actually Grignard reagent is referred to as a kind of a compound containing an alkyl group and an MgBr, right? So alkyl halides are actually contains an alkyl group with a Br. No? If a Br is connected to the alkyl group, it's an alkyl halide. If kind of a MgBr is connected to the alkyl group, it is called as the Grignard reagent, right? This is your Grignard reagent, right? This is your Grignard reagent. This is also a Grignard reagent. This is kind of special Grignard reagent, right? Anyway, it is referred to acetylenic Grignard. Anyway, simply the Grignards can be made like this. Just 2 alkyl halide, add some magnesium in dry ether medium. Magnesium in dry ether medium. So that you will come up with the Grignard reagent. MgBr connected to alkyl halide. That is how we are supposed to produce the Grignard reagent. This is right now. This is how we are supposed to produce the Grignard reagent. Right? Before we are to discuss about the conversions, we should know how to produce the Grignard reagent. Okay, that is it. Preparing the Grignard reagent, right? Then we'll discuss about the reactions involving with this Grignard reagent. Let's discuss about the reactions involved with this Grignard reagent, right? The idea is this, Lama. Idea is this. With these Grignard reagents, these reactive carbons, the functional carbons are actually negatively charged, negative delta. See, with this polarity, the electrons are attracted towards the carbon because magnesium is kind of electropositive element. Carbon is 2.4, 2.5, magnesium is 1.2, the electronity. So electrons are attracted towards the carbon. So carbon is bearing some negative charge there. Negative carbons are produced with the Grignard reagents. It's very important, no? The carbon is negative in your Grignard reagent. So these negative carbons could be used to attack to positive carbons in your organic compounds. These negative carbons in your Grignard reagent can be used to attack to positive carbons. Attract to positive carbons in your organic compounds. Let's see how that is used. Right? So I'll erase this one and I'll use this Grignard reagent to attack to positive carbons in organic compounds. You can use the other thing as well, right? I'll go with this one as example, right? So this is how we make, and let's come up with the reactions possible or reactions important for conversions. So this Grignard, right? This Grignard can be used with organic compounds with positive carbon. See the examples. If you are with a aldehyde, see, if you are with aldehyde now, this is your aldehyde, right? If you are with aldehyde, see what will happen if you add the Grignard to here. If you add the Grignard, this one, CH3, CH2, okay, MgBr, you add in this thing, right? Normally Grignard will be added in the dry ether medium, and normally acidic makeup is needed, H plus H2O. That is how the Grignard is added. See what will happen. So you have the negative carbon here. You have the negative carbon here. So this carbon is positive. This carbon is positive in your aldehyde. In your aldehyde, this carbon is positive. Right now? Because the electrons are attracted towards the oxygen, no? This carbon is positive. Right? This carbon is positive. Then what will happen? So leaving this MgBr, this carbon comes towards this carbon. This carbon attracting towards this carbon. This will first remove this MgBr, and because it's negative, no? Negative guy will attract to the positive guy. Remove this MgBr and just coming to here. Then what will happen? So this carbon can't bear 5 bonds, no? Already that is with 1, 2, 3, 4 bonds. Already that carbon is with 1, 2, 3, 4 bonds. So when this carbon coming towards the aldehyde to make a new bond, this guy has to release its most weakest bond. That is your 5 bond. So that 5 bond will be break like this. The 5 bond will be break like this. So what will be the ultimate product there? So you will come up with CH3, C, 5 bond has been broken, right? The CH is there. To that carbon, this thing is connected. That carbon, this thing is connected. So if you need to write it, you can write like this as well. This thing is connected. CH2, CH3. Right now? This becoming OH minus, after adding the H plus H2O, that guy will become OH. So with this electron movement, this becoming OH minus, no? After adding H plus H2O, the H plus, it will become OH. That is the product. That is how Grignard reacts with the aldehydes. Right? Let's do for another one. Grignard is able to react with aldehydes, ketones, acid chloride and esters. Let's discuss about the stuff, right? So this is how it reacts with aldehydes. See the same thing with the ketones. You would have this ketone like this. This is your ketone. Right? A ketone here. See what we'll do. This Grignard guy. If you add this Grignard, so actually no need to add the same Grignard. We can use any kind of a Grignard, right? I'll come with any other Grignard, right? Okay, see, you are with this Grignard now, right? You are with a new Grignard, not this earlier Grignard we had made, some other Grignard. Okay, see, you are with the same GBR. This is your Grignard, and some CH3. Some CH3 here as well, and some CH3 here as well. Now, Grignard. This is your Grignard, na? In dry ether medium, UID. Some other Grignard, na? H plus H2O is also added. Grignard is always added like that, right? One Grignard, dry ether, then 2 H plus H2O. See, what is the product here to form? This is your Grignard carbon. That is negatively charged. This carbon is positively charged because the electrons are attracted towards the oxygen. This guy is positively charged. So what will happen? These two will get connected. So that this guy has to leave a bond, that is this bond with the MgBr. And this guy is also has to leave a bond, that is this 5 bond. Right? So the molecule is like this now. So you have the OH. That O becomes OH after adding the H plus. This O minus becomes the OH after adding H plus. And these two carbons will connect. And this CH3 comes down. When this carbon guys comes here, this CH3 comes down like this. Okay? This CH3 comes down. And this guy will connect to here. See the connectivity here. Here as well. The two carbons. See the connectivity. This is the Grignard carbon. The Grignard carbon is with 3 R groups, 3 CH3 groups. See? 3 CH3 groups. Right? These are 3 CH3 groups. CH3, CH3, CH3. See the compound, how the Grignard do its work. So Grignard is able to attack to these positive carbons, right? These Grignard stuff come into here, the carbon, leaving the MgBr. Because then these two carbons are to be connected, this guy has to leave a bond as well as this guy. This guy leaves the MgBr bond and this guy leaves the 5 bond, double bond, right? 5 bond. Right? So that is the Grignard connection. So like this, Grignard is able to react with organic compounds to make some compounds with more carbons added. More carbons added. You are starting with 1,2 carbon compound, you are ending up with 4 carbon compound after reacting with the Grignard reagent. You are here starting with 3 carbon compound and you are ending up with some more carbons added to that compound. So Grignard reagent can be used to produce compounds with more carbons added. Right now? Okay? This is some method. So Grignard can be used with aldehydes as well as ketones. Some 2 other things are there, right, to react with Grignard. The acid chlorides and esters. We'll discuss those 2 things as well, and then we can go for the conversions, right? Okay, aldehydes, ketones, acid chlorides and esters, right? Okay, let's have a quick screen capture if you need about this, right? We'll discuss how the Grignard will be reacted with the acid chlorides and esters, right? These theories will be used in conversions, right? See, say you are with acid chloride. Acid chlorides are also with those positive carbons, Cl. Let's come up with some Grignard. Let's say you have this Grignard, CH3, that earlier Grignard. Take the earlier Grignard. This one we had made. This is added with let's say dry ether medium. 1, 2 is adding H plus H2O. Right? See what will happen? Sorry. See what will happen? So this is acid carbon, acid chloride. This is acid chloride. Right? Here this carbon is positive because of this electron attracting towards the oxygen. This carbon is positive. This carbon is negative because the magnesium carbon electrons are attracted towards this carbon. This guy is negative. So what will happen? This negative guy will attract towards the positive guy. Right? There, the weakest bond will break first of all. But Lamai, in acid chlorides, some special thing happens. In acid chloride, some special thing happens. What is that? Not only releasing this 5 bond with the oxygen, but also this carbon will also leave. This carbon will also leave. This carbon will also leave. In our characteristic mechanisms, we have learned that. Do you remember? The chlorines are referred to as good leaving groups. The chlorines are referred to as good leaving groups. Right? So not only this 5 bond, but also this chlorine will leave. That means this carbon is going to actually lose 2 bonds. This carbon is going to lose 2 bonds in this whole procedure. So that what will happen here? As this carbon is losing 2 bonds, the reactive carbon of acid chloride is going to lose 2 bonds. This is the carbon. Then instead of those 2 bonds, 2 Grignard sections will attach. 2 Grignard sections will attach. See, this is the first Grignard section. This is the first Grignard section. CH and 2 CH3s. CH, 2 CH3s. This is the first Grignard section attached. And it has to attach another Grignard section, right? As that acid chloride carbon uses 2 bonds, it needs 4 bonds ultimately, yeah? So 2 Grignard sections will attach here, there. Some CH3 and CH3. See? 2 groups coming from the Grignard. This is very special, na? Very special. With acid chlorides, you get 2 groups coming from the Grignard. This and this. 2 similar kind of groups coming from the Grignard. That is very important in conversions. We'll do so. We'll do those conversions later. 2 groups coming from Grignard. See? All the things are in your note, right? See the note as well. 2 groups from Grignard. 2 groups from Grignard. Right now? That is how the acid chloride behaves with the Grignard. This is just a theory part, right? Okay. We are going to use these things in conversions. What about the esters? Esters are also doing the same thing, Esters are also doing the same thing as acid chlorides. Esters are like this. Esters are like this, right? Any kind of a CH3 group or any kind of R group could appear there, right? ORs, right? Esters. Esters are also doing the same. Let's think of such a situation, right? Let's apply the same thing. Let's apply the same thing, right? Let's apply the same thing. Oh, any other thing, right? It is better to come up with any other one, right? Okay. So you have this one. This Grignard you are dealing with. Some simple stuff than the earlier case, right? In dry ether, you are adding NH plus H2O. So same kind of a reaction possible with esters. So this is your Grignard carbon, which is negative. This is your ester carbon, which is positive. So basically then this guy connects with this thing. This one will leave. Not only that, this is also leaves. 2 of these guys comes. 2 of these guys comes. 2 of these guys comes. When one thing comes, one bond leave, and the second thing comes, the next bond also leaves. These guys are good leaving groups now. When this thing comes, first this thing will. Then the second thing comes, this will leave. So leaving groups are very keen to leave now. When this guy comes for the first time, this thing will leave, and when this guy comes for the second time, this thing will leave. The bond, 5 bond, right? Altogether 2 things will attach. See how to come up with the ultimate compound. So you have this section CH3, see this becoming OH, this becoming OH, see, clear now? This becoming OH, ester carbon, right? The O minus ultimately becoming OH now with the HH plus added. So to that carbon, 2 groups from Grignard will connect. 2 groups from Grignard will connect, right? These 2 are actually Grignard carbons. 2 groups from Grignard, right? So with the Grignard carbon, you have 2 hydrogens and a CH3. This is carbon. You have 2 hydrogens and a CH3. 2 hydrogens and a CH3. 2 hydrogens and a CH3. See, 2 groups are coming from Grignard. This is the R section of Grignard. Right? See, 2 groups from Grignard. Two groups from Grignard. Right now? So with acid chlorides and esters, you are able to produce some compounds with more carbons added. With more carbons added, as Grignard is going to provide 2 groups. towards the acid carbons, right? Okay, so that is how the Grignard is used in reactions to elongate in the carbon chain, to elongate the carbon chain, right? The idea is clear, right? Now let's use this stuff for our conversions. See how to use this stuff in our conversions, right? Okay, so I think it is okay. Let's do some example conversion to use the Grignard, right? Okay, the Grignard method. See, Lamai, I think you are very clear with acid chloride and esters. You are actually adding two groups from Grignard, but with the ketones and aldehydes, you are adding just one group from the Grignard, right? That is clear, no? That is in your note as well. With the acid chloride and esters, you are adding two groups from the Grignard, but with the aldehydes and ketone, you just add only one R group from the Grignard, right? So keep it that in mind. That will be very important in doing the conversions, right? Okay, right. Right, let's do the example. Example 1 for the Grignard's conversions, right? Grignard with aldehydes and ketones. I'll do an example for Grignard with aldehydes and ketones, right? Let's see. You are starting with this one, right? Starting with this one, and you are supposed to produce. See this one. You're supposed to produce this one. Okay, right. Let's use the Grignard technique to do this conversion. Right? Let's copy the Grignard technique to do this conversion. Right? We are supposed to copy the Grignard technique to do this conversion. Right? Okay. Right. The conversion is like this. What is the first thing to do? First thing is coming up with the correct carbon skeleton. So how come? So you have this carbon skeleton at the start. You have this carbon skeleton at the end compound. I'm just seeing only the carbons, right? Just coming up with the correct carbon skeleton. I'm not seeing any bromines here. Don't look at the bromines. Don't look at them. Just look at the carbons. Our first task is to come up with the correct carbon skeleton, right? That's it. Don't look at those look at those makeups. Makeups වලට අහු වෙන්න එපා මොකද ළමයි. මේකප් දිහා බලන්න එපා. මේකප් ටික පස්සේ දාගන්න පුළුවන්. හරිද? මුලින්ම හරියට කාබන් ස්කෙලටන් එක හදාගෙන ඉන්න ඕනේ. හරි ඊට පස්සේ අර මේකප් දාන්න පුළුවන්. මේකප් වලට අහු වෙන්නේ නැහැ. මේකප් කියන්නේ අන්තිමටම කරන වැඩේ. හරි BR ලා දාන්න යන්න එපා මුලින් කරන්න ඕනේ මොකද්ද මේ 3 කාබන් එක මේ වගේ 6 කාබන් ස්කෙලටන් එකක් හදාගන්න එක කරන්න ඕනේ මුලින්ම. මේ ෂේප් එකට හරි. මේව ලීනියර් තුනක් තියෙන්නේ. මෙන්න මේ ෂේප් එකට 6ක් හදාගන්න ඕනේ. ඒක තමයි පළවෙනි වැඩේ. ඒක ඉවර වුණාට පස්සේ තමයි මේව හිතන්නේ. ඒක ඉවර වුණාට පස්සේ වැඩක් තියෙන. ඒක ඉවර වුණාට පස්සේ මොකද කරන්න ඕනේ? coming up with the correct functional carbon. ඒකත් ඉවර වුණාට පස්සේ තමයි මේකක් දාන්නේ. ක්‍රමතුරට ගාන පිළිවෙලට යන්න ඒ ස්ටෙප්ස් තුන ගානට follow වෙන්න ඕනේ. හරි? ඒක හරියට කරොත් වැඩේ ඉවරයි. Right. Let's do. So we are starting with this kind of carbon skeleton and we are supposed to create this kind of carbon skeleton ultimately. After that we can do the makeups. Right. Okay. Right. So we are going to use this Grignard technique, Grignard method to come up with this correct carbon skeleton. That is what we are going to do now. We are going to use the Grignard technique, Grignard method to come up with this carbon skeleton. Right, let's see. So we are starting with a 3 carbon skeleton. We are ultimately having a 6 carbon skeleton. We are going to use the Grignard technique, right, to come up with this carbon skeleton. Right. So first of all, right, actually this is like a building blocks game, Lavan. This is like a building blocks game. In your small ages, right, you may have right, played with those building blocks, no? Neither. Building blocks sellan karane podi kale. Hari sellan karane podi kale sellan karane building blocks hari. Building blocks game එකක් හරි මේක හිම case එකක් මේක. හරි. Suppose you have provided only, right, 3 carbon blocks. 3 carbon blocks. අර තියෙන්නේ building blocks නේ. දැන් මතක නැද්ද ඒවා? පොඩි දැන් ලොකු කට්ටිය එන්නේ මතක නැද්ද? තියෙන්නේ මෙහෙම building blocks. තියෙන නේද? ඔයාලා තියෙන්නේ 3 carbon blocks විතරයි 3යි. Suppose you are given only 3 carbon blocks, right, and you are asked to come up with this 6 carbon block. You are only given 3 carbon blocks. You are supposed to come up with a 6 carbon block. All the inorganic regions are available, no? No carbon blocks are available, but only all the inorganic things are available with the 3 carbon blocks. With the 3 carbon blocks, right? Hurry. Right. See how to do this stuff. So you have 3 carbon block, and you are supposed to build a building with 6 carbons. You are supposed to build a building with 6 carbons. You have 3 carbon blocks. Okay. What you need to do? First of all, try to find the connectivity here. Try to find the connectivity here. That means, first of all, break this whole compound into 3 carbon blocks. Break this compound into 3 carbon blocks. Now, suppose you are given only 3 carbon blocks, right? You don't have 2 carbon blocks. You are only provided this 3 carbon blocks. Knife මුකුත් නැහැ. හොඳේ blocks කපන්න බෑ. Blocks කඩන්න බෑ. එහෙම those reactions are not available in our syllabus, right? Shortening the chain, such reactions are not available in our syllabus. You can only elongate the chains, right? Okay. So you are provided 3 carbon blocks. So first, break this into 3 carbon blocks. That is what you need to do. So let's break it. Let's break it down. Yes, this is the only break what you can do for 3 carbon blocks. මේ වෙන තැන් වලින් break කළා හරියන්නේ නැහැ ළමයි. අනිවාර්යෙන් block 3 carbon blocks නම් උතරින් තමයි ඔයාලට ගලවන්න වෙන්නේ. So that means you are with 2 3 carbon blocks, and the 3 carbon blocks are connected via these 2 carbons. You have 2 3 carbon blocks, right? The center carbon of the left hand block is connected to the corner carbon of the right hand block. That is the connectivity. Identify the connectivity correctly. So we have 3 carbon blocks, right? 6 carbon building is there to make, right? So first of all, you have to break this thing into 3 carbon blocks. Why 3 carbon blocks? Because we are only with 3 carbon blocks. That is why first we are breaking this into 3 carbon blocks, right? Okay. So then we can clearly see this is the connectivity. This is the connectivity. The center carbon of the left hand block is connected to the corner carbon of the right hand block. Corner carbon of the right hand block. So we can suppose, right, this one group out of these 3 carbon blocks, one group, the one block is coming from the Grignard, and we can suppose the other group or the other block coming from the carbonyl compound. It could be the aldehyde or a ketone. So one block is coming from the Grignard and the other block is coming from the carbonyl compound. This could be coming from the Grignard, then this could be from a carbonyl compound. That means aldehyde or a ketone. If this group is coming from the Grignard, if this block is coming from the Grignard, this should be the aldehyde or a ketone, right? So we can suppose like that. So we are trying to come up with the correct carbon skeleton here, right? Okay. So this carbon-carbon connectivity is done through the Grignard. That is what we are supposed, right? Okay, let's do the stuff. So let's take this one. Let's take this one coming from the Grignard. Let's take this one coming from the Grignard. Right? Let's take that like that. I am taking this one coming from the Grignard. But this section coming from the Grignard. So this is the carbon bearing the MgBr. This section is coming from the Grignard. So this is the reactive carbon which bears the MgBr before the connection, before connecting. So then if this is from Grignard, this block should be from carbonyl compound. Carbonyl compound. So in this case we clearly see as this is the carbon which is going to be bear the double bond oxygen. So Grignard carbon connects with the carbon with the double bond oxygen, right? Remember that? Remember what we have learned earlier? Grignard carbon always connects with the carbon which bears the double bond oxygen, right? So this should be the carbonyl carbon which bears double bond oxygen. So that for that carbon you have two R groups. For the double bonded oxygen carbon you have two R groups. So that this should be the ketone. This should be the ketone. So with the double bond oxygen carbon you have two R groups, that is ketone, right? If only one R group is there, that is aldehyde. So this is ketone. Now the thing is that if you are to connect this Grignard reagent where MgBr is bearing on this carbon to this ketone, then our carbon skeleton is done. That's it. See how to do that stuff? How to do that stuff, right? First draw this carbonyl. First draw this carbonyl compound. First draw this carbonyl compound. It is like this. I'll draw it here. I'll draw it here. So this is the carbonyl carbon. So I'll write it here. This is the carbonyl carbon. This is the carbonyl carbon. This is the carbonyl functionality. This carbon. Carbonyl functionality. Always carbonyl functionality come up with a double bond oxygen. And to that carbonyl carbon, two R groups are there, two CH3 groups are there. Two CH3 groups are there. See? That is your carbonyl compound. That is your carbonyl compound which was responsible for making this carbon skeleton. Right? You are supposed to react that carbonyl compound with this one, this Grignard. What is the Grignard? This is that carbon. This is that carbon. We are in the MgBr, the Grignard. So to that carbon, this R group is connected. This R group is connected. Don't look for the other things. Just concentrate on that carbon and the R groups connected to that thing. At the first step, we are only supposed to copy the correct carbon skeleton, right? Don't look at these makeups. No worries. Makeup වලට අහු වෙන්න මෙපා. මුලින්ම හදාගන්න ඕන carbon skeleton එක. ඒක හදලා ඉවරනට පස්සේ මේක makeup දාගමු. පස්සේනේ makeup දාන්නේ. At the last step, no? Right? Changing the functionality, functional groups. Right? So with this carbon, only this R group appears. That is what we see for the carbon skeleton. This R group. Always only add the R groups and the hydrogens with this carbon. Don't add any other thing, right? So this carbon contains this R group, CH2, CH3. Right? Now you see, this carbon is lack of 2 bonds. For carbon, you should have 4 bonds. For carbon, you should have 4 bonds. This carbon is lack of 2 bonds. Only 2 bonds are there. So that add some 2 hydrogens there. Add some 2 hydrogens there. As that carbon was lack of 2 bonds, add some 2 hydrogens there. To make it 4 bonds, add the remaining hydrogens. To make it 4 bonds, add the remaining bonds as hydrogens. Done. Now connect the 2. That's it. Now connect the 2. With H plus H2O, connect the 2. Then what 11? See? What 11? these two things are going to be connected. This will cancel off with one of the bonds here. Right now? This will cancel off with one of the bonds here. So let's write that thing. You have the CH3. You have this carbon as OH, coming as OH ultimately. That is this carbon now. Then write this thing, this CH3, as you see in the final product, that's CH3, right? Just bend this one and write, as you see in the final product. That is our major task. So to that carbon, the Grignard carbon is connected. This is the Grignard carbon, see? As MgBr leaves, that carbon is with 2 hydrogens and a CH2CH3. 2 hydrogens and a CH2CH3. Right now? So that is your skeleton. Skeleton is made. We are happy now. Skeleton is made. See? Skeleton is done. So this is the heart of the question, Lavai. This is the heart of the question. If you have done this thing, now note number 1, 2 and 3 will give you the final compound. That's it. If you have done this thing correctly, you are done naturally. This is the heart of the question. Now can't we make these two guys from here? This is 3 carbon stuff. This is also 3 carbon stuff. Even this one is a 3 carbon situation. So you can come up with the MgBr, the Grignard, by first having that Br here, no? First having that Br at the same carbon. If you add magnesium triether, you will come up with the MgBr. So can't you complete from here to here? 3 carbon situation, anti-Markovnikov. Can't you complete from here to here? After the skeleton is done, can't you complete? So the same skeleton is there. What you should do? So to come up with 2 BRs, first of all you should have some double bond here. Just to do some dehydration. Getting rid of water molecule. Then add the 2 BRs. That's it. Do some dehydration. Congestion heating. Then add some 2 BRs. Actually the question is done lamai දැන් ඉතින් ඔයාලා මේක ටික දාන්න තමයි තියෙන්නේ. The hard stuff is done. Final shot. Just to add some Br to CCl4. Right now? What about these two? You can clearly complete the stuff now. This is functional at the corner. So anti-Markovnikov is needed. Functional to the corner. Functional to the third carbon, corner carbon. Anti-Markovnikov is needed. R2O2HBr. Here the functionality has the center. So functional center means Markovnikov addition. To add some H2 molecule, you can come up with DIL H2SO4. Finally, this stuff, BCC. See how easy the conversion is, right? So it is all about analyzing the final stuff, final molecule with the starting compound. Right now, okay. So I'll do the same conversion by taking the Grignard here and carbonyl here as well. We can do so like that. We can do the same like that as well. So we'll do that thing. First copy this one. Oh, you can have screen capture first of all. Right, happy let's do the same conversion. Right, let's do the same conversion. Taking the Grignard here and the carbonyl here. Earlier we had done this conversion, right? Taking this section, this block coming from the carbonyl and this block coming from the Grignard. Taking like that, we had done the conversion earlier. Now let's do the same stuff, right? By taking this section as the section came from the Grignard and this section as the section came from the carbonyl. Let's do the stuff, right? Okay, let's start from the beginning, right? So we clearly see you are starting with a 3 carbon block, and you are ending up with a 6 carbon block. So we have to use some technique which will elongate the carbon chain by more than 1 unit, right? As we are starting with 3 and ending up with 6, we should use a technique which will introduce more carbons to your chain. So there are 3 methods available like that: Grignard method, Acetylide method, and the condensation. Here we are supposed to use the Grignard method, right? Let's use that Grignard method. So first of all, what we need to do? First of all, we need to break this final compound into 3 carbon groups. Break this final compound into 3 carbon groups. Why is that? Because only 3 carbon groups, 3 carbon blocks are available with me, right? So first break this one into 3 carbon blocks like this, right? Okay, then identify the connectivity. Correctly identify the connectivity. These 2 carbons are the ones which had been connected to form this larger compound, these 2 carbons. Okay, this time around we are going to take this one coming from the Grignard, this block coming from the Grignard, so that this is the Grignard's functional carbon which bears the MgBr, and this block coming from the carbonyl. So this is the carbonyl carbon which bear the double bond oxygen. So those 2 are the ones which will connect now. So we clearly see with this carbon only one R group is appearing, so that it should be the aldehyde. The carbonyl group, the carbonyl compound with only one R group, this group, aldehyde. Let's come up with the heart of the question, right? First write the Grignard here. The one at the left hand side, just write that thing at the left hand side. One at the right hand side, just write that thing at the right hand side. Then it is very easy to connect the 2 guys to come up with the correct carbon skeleton. Yes, let's start with the Grignard because it is at the left hand side coming first, right? So this is your Grignard carbon. So with the Grignard functionality. This is the Grignard carbon with that functionality, MgBr functionality. Grignard functionality is that, no? So with that carbon, you are with 2 R groups. With that carbon, you are with 2 R groups. See, CH3. The 2 R groups are 2 CH3 groups, right? The CH2 groups and these CH3 groups. 2 CH3 groups, right? Not any other. And you clearly see this carbon is lack of 4 bonds. Only 1, 2, 3 bonds are there. So you need to come up with a hydrogen there. 1 hydrogen should be added as the 4th bond. Earlier you had 3 bonds only, the 4th bond as a hydrogen. That is your Grignard. That thing is supposed to react with this carbonyl compound. See, this is the functional carbon of the carbonyl compound. So that is this, which bears the double bond oxygen. So to that carbon, only this R group is connected. CH2, CH3, that R group is connected to this carbon. To the with this block, only for that carbon, only this group is connected because this is a 3 carbon block, no, right? So CH2, CH3, right? So we clearly see this guy is lack of 4 bonds. This guy is lack of 4 bonds. 1, 2, 3, only 3 bonds are appearing. So put some hydrogen there. Put some hydrogen there. Put some hydrogen. You can add the hydrogen here as well, right? No worries. Only one hydrogen should be added to the carbon to give it a 4 bond situation. Now just connect it to these two guys. Just connect these two guys, right? With the addition of H plus H2 as well. So then not 11. Let's write the stuff, right? So these two guys will connect. These two guys will connect. While this thing will leave, as well as one of the bonds from here. Right? That is the idea. So let's connect the stuff, right? So this is your MgBr carbon. This is your MgBr carbon. You have two CH3 groups there with that carbon. The other CH3 is down. And some hydrogen is also there with that carbon. So we see MgBr leaves, right? With this carbon, two CH3 groups and a hydrogen is there. Just look at the final compound and write, right? With the same shape, just write. Then to that carbon, this carbon is connected. To that carbon, this carbon is connected. This is that carbon. The carbonyl carbon. This is the carbonyl carbon. So there, the double bond oxygen becomes OH. With this hydrogen it becomes OH. Then to that one H and a CH2 CH3 is there. See, that is your heart of the question. Now we are done now. Now we are done. You see, things are done now. Nothing much to do. All the hard stuff is done now. All the hard stuff is done. Right? So you have this skeleton. You have the correct carbon skeleton now, like this, as the product. What you need to do? You need to come up with 2 BRs at these two carbons. What you need to do? Just get rid of some water molecule. That will bring some double bond here. And then come up with some Br2 addition. That will give some 2 BRs to these two carbons. That is very simple, right? Okay. Let's complete that thing. A simple process, right? Conc H2SO4 and heating will give you the double bond. Right? Then directly you can finish the stacks by adding Br to CCl4. Here, what we do? So before coming up with the MgBr, right? You should have some Br there. You should have some Br there. Before coming up with the MgBr, you should have some alkyl halide there. To alkyl halide, you just add the Mg diethanol. That is how the Grignard is formed. So this is very straightforward. This is very straightforward. What we need to do here? Just add in some HBr. Just add in some HBr. The Br to the center. Markov. Here you have some oxygen carrying at the corner carbon. So function should bring to the corner carbon first of all. Function should be bring to the corner carbon first of all. So for that, first you need to come up with the anti-Markov. You need to come up with some anti-Markov addition. That will bring you the functional to the corner carbon. Like that. The R2O2HBr. Then you can convert this into OH before converting it into the aldehyde. Convert that into OH, and that thing will give you the aldehyde by adding PCC. This OH can be added by just adding aqueous NOH. Right now? So that is your final conversion. Done now? So you can complete this one. Right? And then do some work, some conversions available in your tute. Let's complete this one. Then we can do some questions. Done? Right. So we had a problem, right? Oh, and I would duck. I said to me. මේක පැහැදිලිනේ මොකද උනේ කියලා. මෙතන උනේලාම මේ දෙන්න බ්‍රේක් කරගත්ත දෙකට, right? So මෙයා Grignard carbon උනා. So that was the carbon. And that carbon is with 2R groups. That carbon was with 2R groups. The 2 CH3 groups. Done? As that carbon is lack of 4 bonds, then I have added a hydrogen. R groups දෙකයි MgBr එකයි bonds 3යි තිබ්බේ. I have added an hydrogen. Then for this one, this carbon is the functional carbon, right? This is the functionality. It is not because of this thing I have written this one, right? This is the carbonyl functionality, right? It's not because of this group appearing I have written like this. This is because of the carbonyl functionality. I just written it as the double bond oxygen. And you have this R group, and as it is lack of 4 bonds, I have added one hydrogen, right? Okay. So then we are supposed to connect these two guys. So when these two guys are connected, this MgBr leaves and one of the 5 bond will leave. So we are writing like that, right? So that did not really happen. CH to CH, this thing, and this is this carbon, and this becomes OH, and it is with some hydrogen and a CH2 CH3, hydrogen and a CH2 CH3. Right now? So we are done with the carbon skeleton. We are very happy now. We are done with the carbon skeleton, right? We are very happy. So now this is actually the heart of the question, right? So you no need to box this stuff, right? That is the heart of the question, right? So then we can come up with this one by just one single step, right? Just add some PCC. It will convert to this ketone. Or one can come up with H plus came in for as well. H plus came in for as well. Right? So to make this one, first of all you should have some Br connected to the center carbon. You should have some Br connected to the center carbon. Then only you can connect it to the MgBr. MgBrs are made by alkyl halides by adding some magnesium diether. So this could be done very easily with some Markovnikov addition, because Br comes to center carbon, and here we should come up with a corner functionality. For that, first of all, functionality should be taken to the corner position. So for that, kind of anti-Markovnikov is needed. Anti-Markovnikov is needed. R2O2HBr. Then we can convert this Br to OH and aldehyde ultimately. It is simple stuff now with the use of node number 2 and 3. Just node number 2. Br converted into the aldehyde. So this is just by PCC. This is NOH. Aqueous. Right? So that is your conversion. Right? Okay. We are moving to the second method. The second method of elongating the carbon chain by more than 1 unit. Right? That is the Acetylide technique. Right? It is written as the technique number 1 in your tute. In your tute, it is written as the technique number 1. Right? Acetylide method. Acetylide method. acetylide method. See what is available there in your note. Right, first of all, acetylide technique. See, sorry. Let's discuss about the acetylide method, right? First of all, I'll discuss the theory behind the technique, right? How the acetalides are made and how those can be used to come up with compounds with more carbons. Let's discuss the two things, right? Actually, we have discussed these things as when we are doing the terminal alkynes and the stuff with the alkyne chemistry. Again, I'll give you some recap, right? Okay, first, how the acetalides are made. Basically, acetalides are made by terminal alkynes, right? Basically, by terminal alkynes, the acetalides are made. See, first you need to come up with a terminal alkyne. See, this is a terminal alkyne. The triple bond at the terminal position. With this, you can form the acetalides. Acetalides are like this. These ones are the acetalides, right? To come up with these acetalides, what you need to add is actually the sodium or the NaNH2. One of those things can be added, right? This is how you're supposed to make the acetalides. See, some other example. You can make acetalides with any kind of terminal alkyne, right? See, you have this one. This is another terminal alkyne. Terminal alkynes are the compounds with triple bonds at the corner position. Triple bonds with corner carbon, right? You can make the acetylide from this one as well. These are the sodium acetalides. Some minus carbon will appear. So what you need to do is just adding some sodium or NaNH2. It will produce some acetalides, right? This is how you produce acetylide, right? Okay. Let's discuss how these acetalides can be reacted. How this acetylide can be reacted to come up with compounds with more carbons. To come up with compounds with more carbons, how these guys can be used. Let's discuss. Right? Let's discuss about that thing. Right. Okay, I'll come up with this one, right? I'll use this acetylide, right? So reactions involving acetylides to make compounds with more carbons. See, basically in these acetylides you are with a negative carbon. These acetylides you are with a negative carbon. See, negative carbon. So that carbon can be used to attack positive carbons in your organic compounds. This carbon, the negative carbon, as a nucleophile, you can use to attack to positive carbon centers in your organic compounds, right? So this is a nucleophile, right? The nucleophile. So this can be used to attack to positive carbons. Like in Grignard, this is also able to attack to positive carbons in your organic compounds. See? So if you have with a alkyl halide, see, that guy carries some positive carbon, right? To this positive carbon, to this positive carbon. This positive, because the electrons are carried towards bromine, right? So this carbon is positive. To this positive carbon, right? You can attack by a sodium acetylide. You can attack by a sodium acetylide. See, if you add this thing, CH3, I'll add like this, no? Both are same. I'll add the same compound, no? This one, like this. Is minus. Just like this sodium acetylide, right? Then what will happen? You have this minus carbon here with the acetylide. So that carbon will connect with this guy. Leaving the sodium, that carbon will connect with this guy. As this carbon is forming a bond with this one, this halogen will leave. This halogen will leave. This halogen will leave. The halogens are very good leaving groups. When this carbon connects with this carbon, this halogen will leave. See how the compound looks like ultimately. CH3 is there. So you have this carbon coming from the alkyl halide, and it is with a CH2 group and H. It is with a CH2 group and H. So I'll bend that CH3 group and H, and to that carbon, this C is connected. This C is connected from the slide. The C is connected from the slide, and it is with a triple bond. It is with a triple bond and C and CH3. This carbon is a triple bond C and CH3. So you clearly see some compound with more carbons are made, some compound with more carbons are made. This is kind of negative positive attraction. As this guy connects with this carbon, it will leave this sodium there, and as this carbon is making a new bond, it has to leave one of the existing bond, that is the CBr bond, which is polar, as Br is very keen to leave, considered as a good leaving group. Right now? So with alkyl halides, we can use acetylides to come up with compounds with greater number of carbons. Not only with alkyl halides, but we can use aldehydes and ketones as well to connect these acetylide groups. Right? See, if you have the aldehyde like this, like in Grignard case, right? With the aldehydes and ketones, you can use the acetalides. This is your aldehyde. You have a positive polar carbon like this. This carbon is positive polar, and you are supposed to use some acetylide here. This acetylide, this come with the different acetylide, different one. See, this is acetylide carbon. This is a functional carbon, acetylide carbon. Let's come up with some new acetylide. Right? So what will happen? These two things will connect, leaving the sodium from this side, and from this side, this 5 bond will break. That 5 bond will break. So you will end up with this one, CH3. This is your carbon, which will come up as O minus ultimately because of this electron movement, and that carbon has a hydrogen. That carbon has a hydrogen, and this carbon will be connected to that. As that carbon will be connected to that. See, with a triple bond and the rest. The triple bond and the rest. So if you are to add some H plus H2O, if you add some H plus H2O like in Grignard, If you add some H plus H2O like in Grignard, so you can come up with a OH here. You can come up with a OH here. You add some H plus H2O like in Grignard. Right? If you're not adding H plus H2O, this will be as O minus, then that will be connected to this Na plus leaves. It will be connected to the Na plus which leaves from here, as that is a O minus, no? So Na plus leaves will attract towards oxygen to form a salt like this. Both are okay, right? If you need a H here to come up as an alcohol, you can come up with some H plus H2O acidic makeup. Right? No? Not only aldehydes, but also the ketones can be used like this. Same thing, right? Same kind of reaction. Ketones also can be used. I'll come up with some simple acetylide. I'll write the acetylide like this as well. Both same thing, right? I'll write the acetylide like this. Till you should be able to write the product correctly. Right? So what will happen? So this is your carbon, positive carbon. This is your negative carbon. These two things will connect, right? Those two will connect. Leaving the Na plus here and one of the oxygens here, or one of the bonds with oxygen, right? So ultimate compound is going to be CH3 is there, that C is there, and this becomes O minus, and will connect with the Na plus left from the acetylide, and that guy is with another CH3 that can be written at the bottom. Just bend that thing and write that, and you will connect these two carbons. See the two carbons connecting. That guy is with a triple bond, that carbon is with a triple bond, and a C and a CH3. That carbon is with a triple bond, C and a CH3. Triple bond, C and a CH3. Right? That is how the acylides will form some compounds with more than one carbon in it. Right? So acetylide technique can be used to create some compounds with more than one carbon is added. So basically acetylide can be used with the alkyl halides, aldehydes and ketones. Right? Alkyl halides, aldehydes and ketones. Right now, this is the theory part behind this conversion pattern. Right? Okay, let's use this one to come up with some good conversions. Right? Okay. See how we can use this acetylide technique, right, to come up with good conversions. Right, we'll come up with some example conversion here. Right? Here the acetylide method. Let's come up with this conversion. Example conversion. Right? Acetylide method example conversion. Right? Let's try to do this thing. Let's try to do this conversion using the acetylide method. See, the same conversion which we have done using the Grignard technique. The same conversion which we have done using the Grignard technique. Let's do the same thing with the use of acetylide method as well. This is the same conversion we had done with the Grignard. Okay, as the example conversion, this is what I have solved, right? Okay, so I'm going to solve this one using the acetylide method. So acetylide method is actually the method which we use to form this carbon-carbon bond, or to come up with the carbon skeleton, right? Correct carbon skeleton. See how this can be used. This acetylide technique can be used here, right? So you have a CH2 here, no? Right? Okay, first what we should know. First, we have to count the carbons in the carbon skeleton. You have 3 carbons here. You have 6 carbons here. 1, 2, 3, 4, 5, 6. Right? So more than 1 carbon should be added. As we are with 3 carbon blocks, first we need to divide this thing, the 6 carbon block, into 3 carbon blocks, so that this is the only possibility available, right? As we are with 3 carbon blocks, first we need to break this whole compound into 3 carbon blocks, right? So this is the only breaking available then. So the connectivity is between these 2 carbons then. Connectivity is between these 2 carbons. Center carbon of the left hand block is connected to the corner carbon of the right hand block. That is how the new carbon-carbon bond is made to come up with the compound with 6 carbons, right? Okay. So now I am supposed to use the acetylide method to do this conversion, to make this carbon-carbon skeleton, or to make this larger carbon skeleton. I am supposed to come up with the acetylide method. I am supposed to use the acetylide method, right? Okay. So one block is coming from the acetylide, so we can take the other block coming from the alkyl halide. I'll take like that. You can think of the aldehyde ketone as well, but it's easy to go with the alkyl halides, right? So I suppose that one block out of these 2 coming from the acetylide, and the other block coming from the alkyl halide, right? One block from the alkyl halide, the one block from the acetylide, sodium acetylide, right? So here, not like in the Grignard technique, here the block coming from the acetylide group is actually very specific, right? You can't mark both the groups coming as the acetylide. So one group from the acetylide, one group from the Grignard is okay, but the group from the acetylide, the block from the acetylide is very specific. Why is that? Because the functional carbon of acetylide, the acetylide functionality is always coming with the corner carbons. Acetylide functionality, Na plus C minus, that acetylide functionality always coming up with the corner carbons. So that is how, no? That's how the acylides are made, no? First you have to come up with the terminal alkynes. Then you have added some sodium in it too. That's how the acylides are made, no? So basically acetylide functionally comes up with the corner carbons, so that this section, this block can't be from an acetylide. This section can't be from acetylide because the functionality is at the center carbon. But here with this block, the functionality is at the corner carbon. So this block is the block which is coming from the acetylide. To select as the block from the acetylide, the functionality should appear at the corner carbon. To select the group coming as from acetylides, you have to have the functionality at the corner carbon. Remember that. So this is the group coming from the acetylide, and this one then coming from the alkyl halide. See, this is very important, no? Right. So let's do the stuff. Let's do the conversion. So first write the alkyl halide. Let's write the alkyl halide here, responsible for making this larger compound. Alkyl halide. See, this is the alkyl halide functionality. This is the alkyl halide functionality. This is the alkyl halide functionality. Carbon with a Br. That is the alkyl halide functionality, right? So with this functional carbon, you have two CH3 groups attached to that. Two CH3 groups attached to that. As this carbon is lack of 4 bonds, only 3 bonds are appearing now. So remaining bonds should be added as a hydrogen. This is your alkyl halide. This is your alkyl halide. Then the acetylide. Let's copy the acetylide. So acetylide functionality is like this. You have the sodium plus and triple bond like this. This is the acetylide functionality, which is coming up with the terminal carbon, is coming up with the terminal alkyne. H9 functionality, which is coming from the terminal alkyne. So with the acetylide functionality, already 2 carbons have been written. With the acetylide functionality, already 2 carbons have been written. So 2 carbons have been written, right? 2 are written. So only 1 carbon is left. 2 are written with the acetylide functionality. 1 carbon is left. 1 carbon is left. The CH3. Right? That is the acetylide we are supposed to use with this alkyl halide to come up with the bonded carbon skeleton. Right now? That is clear now? With the acetylide functionality, already 2 carbons have been written. So only 1 carbon left to write the CH3. Right? Don't worry about these makeups, right? Don't worry about these makeups. Right? This Br is not because of this Br, right? This Br is not because of this Br. This is a makeup, but this is the functionality. This is the alkyl halide functionality. That is why I put the Br, not because of this makeup, right? After writing that, you have 2 R groups. I just put those 2, and to form the 4 bonds with the carbon, you had just added hydrogen, right? If you connect these two guys, what will happen? These 2 carbons, this is your positive carbon with the bromine, right? So these 2 guys will connect while leaving this one and this Br. That's how the things happen. So you will come up with this skeleton, CH3, C, you have a hydrogen here, and a CH3. This is the alkyl halide functionality, that carbon. As the Br leaves, that carbon will connect with the acetylide carbon, like this. This is the acetylide carbon, leaving this Na, right, and this CH3. Right now? So we are very happy with the carbon skeleton. So carbon skeleton is done now. Carbon skeleton is done. Actually, heart of the question is done. So very simple makeups to be carried out to complete the conversion. Right? Very simple things to carry out. So let's complete the stuff. So you have a triple bond here, and you need to have 2 bromines at these 2 carbons. At these 2 carbons, you need to have 2 bromines, and you have the triple bond here, functionality here. What you need to do? First, you have to bring the functionality to this position. A double bond. Then you can add some 2 Brs to come up with this product, right? Let's do the stuff. So first, bring in the functionality. Addition elimination technique, right? HBr or the H2O technique. Come up with that. First, you need to come up with the double bond. So first, convert the triple bond into a double. Right? So it's a double bond. That can be done by H2PD, barium sulfate, quinoline, Then we need to bring this double bond to here, changing the functional carbons. That can be done by addition elimination technique, note number 3. Adding, removing HBr, so H2Os. Right? Let's add some, right? Deal H2SO4. Then if you are to remove that deal H2SO4, you will come up with a double bond at the position we need. Right now. This can be just done by adding conc H2SO4 to remove some water molecule. Then final step is very clear. To add 2 BRs to these 2 carbons, you can just add some Br2CCl4. Right now, that is done. And with this side, this is straightforward to come up with a Br here. Just add in some HBr, the Markov addition, Br to the center. And here, to come up with the terminal alkyne, so acetylide, first you need to come up with the terminal alkyne. Where you have hydrogen at the position of sodium. At the position of sodium, you should have a hydrogen first. If you have to add some sodium to there, that is how you are supposed to produce this acetylide. So with a double bond, how to come up with a triple bond? Double bond connected to triple bond. First you need to come up with Br2 addition. First you need to come up with a Br2 addition to the double bond. That is the way of producing the triple bond. First you need to come up with Br2 addition, and then you can remove 2 of HBr molecules from that. First you come up with the Br2 addition. Br2CCl4. Then you can remove 2 HBr molecules like this to come up with the triple bond by adding alcoholic KOH. Right now, that is your final conversion. Right? In this case, it is very important to note that when you are choosing the section coming from the acetylide, definitely the functional carbon should be a corner carbon. If you don't have such a functional carbon in your final compound, if you don't have a corner carbon at the as the functional carbon at the connectivity, you can't do such a conversion with the acetylide technique. Right? To select the block coming as the acetylide section, definitely that functional carbon should be a corner carbon. If such a corner carbon is not available as the functional carbon, as the connected carbons in a compound, then such a conversion can't be done by acetylide technique. Remember that. If you need an example like this, so if finally this kind of a compound is have to be made, see, if finally they have asked you to come up with this kind of a compound, see, if they have asked you to come up with this kind of compound, and finally starting from 3 carbon compounds, this is the only breaking possible, no? So that these 2 are the functional carbons, no? Which has been connected, but none of these is a corner carbon, no? This is a center carbon, this is also a center carbon. None of these is a corner carbon, so that you can't do this kind of conversion with the use of acetylide method. Because both the carbons are not corner carbons. If at least one carbon is corner carbon like this at the connectivity, you can use that section as the section coming from the slide. If there is no such corner carbon at the functionality, at the connectivity, so you can't use the slide technique to solve this kind of a question. Slide method can't be used for these, right? For these acetylide method. Can't be used. Right නේද? හරි. ඉතින් ඕක තමයි ළමයි. ඔයාගේ කතාව. This is all about the acetylide technique. Right? This is all about the acetylide technique. Right? So copy this one, and you have much more questions. Right? You have much more questions appearing. Right? In your page number 10. Right? You have much more questions appearing at the page number 10. So you can practice those. Right? So try all of those. All the 7 questions. Basically, you can do the first 5. So you can do the first 5. Some conversions are able to be done with the acetylide technique as well. So use both the techniques what we have learned today. We had learned about the Grignard technique as well as acetylide techniques, right? When regarding the first 5 questions appearing at the question set 2 at the page number 10, all the 5 questions can be done by the Grignard. Do those workings with the Grignard as well, and then some of the questions, some of the problems can be solved with the use of acetylide technique. So solve them with the use of acetylide technique as well. So identifying whether you are able to use the acetylide technique or not is another skill. Identify by looking at the compound, final compound, identifying whether you can use the acetylide technique or not is another skill to develop. So I earlier said that all the 5 questions can be solved with the use of Grignard. Do them with the use of Grignard. Then after that, choose the conversions which can be done by the acetylide technique. You have to identify that thing. Identify the conversions which can be done by the acetylide technique, and then solve them using the technique. Right? That is also a skill to develop. Right? Okay. So then you can take a screen capture here with this one, and we'll stop at this. Just do the work and send the answers to me. Right? Okay. Right, then that's it for today. We'll stop at this stage. Goodbye then. See you next week.